Right, two light bulbs A and B are connected in series to a constant voltage source. When a wire is connected across B, what will happen to bulb A? We've had a similar question before, I think. So if I put a wire across B, and you know what that does to B, what happens to A? And the switch is closing, so it's open here, but you would imagine the switch being closed. You see quite a few of these questions on the test where I don't ask you to do calculations, but I ask you to think about what happens in the circuit, or think about what happens to the current or the voltage in the circuit. Let's stop at 55. 55. All right, A is right. It's going to glow brighter than before. When we had the two bulbs, they split up the voltage, because that's what resistors in series do. But when I take this one away, this one takes the full voltage. So say if this was 12 volts, I'd have 6 and 6. But if I take this bulb away, I have 12 on that light bulb. All right, this is good. Let's see. Which circuit produces more light? Two light bulbs in parallel, two light bulbs in series. Does one produce more light? And if so, which one? All right, we'll stop at 40. Very good. A is right. You got 12 volt, or if you imagine you have this 12 volt battery, you got 12 volts here, and you got 12 volts here. However, over here I have 6 volts and 6 volts. And remember, power is equal to V squared over R. Now I use this expression because R is constant for all of these light bulbs. So if I have light bulbs with a constant resistance, then I can just look at the voltage. And so these have bigger voltages than these, so I'm going to get more power out of these resistors. So what I'm talking about, that's why I use that instead of using this one, which is sort of the more standard, because in this one, it's hard for me to tell because V and I are different for these resistors. They have different voltages, but they have different currents too. Now it turns out that the voltage and the current are bigger for these two, but that's just a little harder to think about. So that's one of the advantages of having these different expressions for the power, because you can look at the different expressions and just pick the one that has the one variable that changes and the other variable remains constant. Sometimes your resistance remains constant, sometimes your voltage remains constant, sometimes it's your current. So you just have to play that by ear, but that's why we have those three expressions. This is a good application of this. So I have these bulbs set up, these resistors. By how much is this bulb brighter or dimmer than this bulb? Is this bulb twice as bright as this bulb? Is it the same brightness? Is it half as bright? Quarter as bright? 4 times as bright? How much brighter or dimmer is this bulb than this one? Now you probably know right off that it's either brighter or dimmer. We just had that question, right? You'll know if it's brighter or dimmer. So now by how much is it brighter or dimmer? They all have the same resistance. All right, you're getting a little bit of dichotomy between two answers. So turn to your neighbor and ask them what they put. And if they put a different answer than you tell them they're stupid. Now don't do that. No, we're in a kind place here. All right, that's a little bit better. I'm going to stop at 130. 130. Nobody's stupid in here. Nobody. Like, we're all capable of doing well at this, okay? All right, 130. Okay, D is right. So remember we have this expression for power is V squared over R. I got 10 volts across this battery, and I got 5 volts across this battery. So the voltage of this one is half that of this one. If I have half the voltage, because it's squared, I have a quarter of the power. So volt B, which you know is going to be dimmer just because it has less voltage, we've already talked about that, but it's actually going to be a quarter of the brightness. It's going to be quite a lot dimmer because you have half that voltage. It turns out, by the way, that P is equal to VI, right? I have half the voltage. I also have half the current. So that's where you get that quarter, but you just sort of have to think about it a little bit more. What is the current? What is the voltage? How are those different? What happens to the voltage across the resistor R1 when the switch is closed? Think about this. This is several little steps you have to make in your mind to figure this out. If I close this switch, which means I'm just adding this resistor, close this, what happens to the voltage across this resistor? And y'all are doing all right. So sure that y'all get this so well, but still about 10 of you have the wrong answer. Why don't you turn to your neighbor and just do your little sign thing where you do the. Huh?
It's a knot.
Oh, is it a knot? Okay. All right, I'm going to stop at 1 minute. All right, good. A is right. Let me step you through this. So a couple ways you can think about this. The first thing you need to recognize that if I close this switch, this resistance, when I add resistors in parallel, the equivalent resistance drops. So this resistance right here is going down. It's going down. It's going to decrease, okay? Because I've given the electricity more routes to go, more paths to travel, and so it encounters less resistance. And so a couple ways, the way I like to think about it is, well, if I add this resistor, the overall resistance of the circuit decreases. The equivalent of the entire circuit decreases. That means my current is going to go up. And if the current goes up, the current goes up here as well. So that then the voltage will go up. Or another way to think about it, this resistance decreases. A smaller resistor carries a smaller voltage. And so if this now carries a smaller voltage, this voltage has to increase because you know the two voltages, rule number 4, has to add up equal to this. Number 4 for series circuits. What happens to the voltage across resistor R4? All right, let's stop at 30. Stop at 30. Okay, good. D is right. It decreases. We've already talked about it a little bit. Let me just recap. This resistance decreases when I add a resistor in parallel. Because the resistance decreases, the voltage also decreases. But if I have these two resistors, that is R1 and R equivalent of 2, 3, 4, I'll call it 2, 3, 4 because it's those three resistors. If this resistance goes down, the voltage also decreases. the only voltage that increases is this voltage. Actually, the current through this one increases. These decrease because the resistance decreases. All right, so a couple more. Which resistor has the greatest current going through it? And you assume here that all the resistors are equal. Remember how current splits up? It splits up when it goes into these parallel branches. And generally, current will take the least resistive path, the path of least resistance. All right, let's stop at 43, or I'll go to 45. D, yeah, D is right, the greatest current. So let's imagine, I don't know, I got 12 amps going through here. I got 12 amps going here. In the top, I'll have how many amps? 6, and 6 here as well. They split up evenly because these are the same. But then over here, on the top, I'm not going to get 6. I'm going to get what? Go up 3. What's it? 4. I'm going to get 4. Look at. She said 2. I got. What did I say? What do we get? 4. Right, because this is the big resistors, and down here we got smaller. These are twice as big, so they get half the current. This one's half as big, so it gets twice the current. So I get 8 amps down here and 4 amps up here. So that path of least resistance at R5 gets the most current. We'll come back to this. Let's see, let's look at, I think we left off with this quick test, if I'm not mistaken. By the way, there is a softball game this evening, right at 5 or 4. When is it? It's different in different places. It's at 4. It's at 4 o'clock. Y'all gonna win? You are? Are they any good? I'm serious, like, are they good? Not as good as you? I think they're from Mississippi right now. Okay. Conference. Alright, so let's try this question right here. In this circuit, what happens to the voltage in each resistor as you add resistors in parallel? So we had this before, but it's asking a slightly different question. If I add resistors in parallel, how does that affect the voltage in the resistors that are already there? Right, so if I add more resistors in parallel, how does it affect the voltage in the resistors that are already there? Does that voltage increase, decrease, stay the same, or does it depend on the value of the resistor that you add? All right, let's stop at 105. 105. Very good. C is right. So let's say I got 12 volts here. That means I got 12 volts here, 12 volts here, 12 volts here, and on and on. It doesn't matter if I add more resistors. I'm still going to have 12 volts. Right? That's like your house. Did you know your house is laid out in series? But it's not, right? It's laid out in what? See, I was trying to see if I catch that, but you did not. You failed my little quiz. Your house is laid out in parallel, okay? And the reason is that so that all of your devices will have the same voltage. It's easier to design devices in that way. So they all have the same voltage, regardless of how many light bulbs you put in that circuit or whatever. So if you turn on another light, all the others don't get dimmed. They still keep the same brightness. All right, let's look at this. What happens to the total current if you add a resistor, as I show here? Does the total current go up? Does it go down? Or does it stay the same? What happens to the total current if I add a resistor right here? Does it go up, down, or stay the same? That is a very similar question, but I think it was a little bit different. Think about what happens to the equivalent resistance of that parallel part, and what does that do to affect the current? All right, y'all are sort of spread out, like you have all different kinds of answers. I want to remind you, when I add a resistor here, the equivalent decreases. So what does that do to the current in the circuit? Oh, let's stop at 110. 110. It's all right. 110. Okay, good. A is right. So remember, the equivalent of this branch decreases when I add that resistor. And so the overall equivalent resistance, it also decreases. Remember, V is equal to IR. If R goes down, I goes up. So the total current, that is the current that's going through this part of the circuit, will increase as I add more resistors to those in series. All right? Let's do this example. I don't know that we've done, I think this is our first combination circuit. You'll see some combination circuits on the test. And some of you did this in lab already. So here I want to know the equivalent resistance. I want to know the voltage and the current for each resistor. All right, you're going to see some circuits like this. You'll see some that are a little more complicated, and we'll do some of those. But let's just do this one first. I want to know the equivalent resistance, the current, and the voltage for each resistor. First, we'll start with the smallest part that's either series or parallel. That would be this part. You say, well, that's a 3 and a 6 in parallel. I know that the equivalent of that is just 2. 1 over 3 plus 1 over 6. That's equal to 2 ohms. And so I like to redraw them. So I got 1 ohm and 2 ohms, 12 volts. You can probably look at the distribution of resistance and say right away that this is 4 volts and 8 volts. If you're not able to do that, let me show you how I did it. I say the equivalent is 3 ohms. So it's 12 volts. That means that I have a current here equal to V over R, which is 12 over 3, or 4 amps. So that means I got 4 amps going here. Now if I have 4 amps going through a 1 ohm resistor, V equal IR, 4 times 1 is 4. 4 times 2 is 8. However, I can also just look at the resistors. I know that these two numbers have to add up equal to 12. And I know that this one will have half the voltage of this one because the resistance is half the resistance of this one. So it has to be 4 and 8. Either way you want to do it's fine. Now if that's resistors in parallel, gosh, what is it? They have the same voltage or current, resistors in parallel. They have the same voltage, right? Just like capacitors, resistors in parallel have the same voltage. So if this has 8 volts, these also have 8 volts. And this guy has 4 volts, which we'd already seen. Like we saw that here, it's carried over. And then, now I know the resistance and the voltage for all 3. I can find the current. And so I is V over R. So my current here will be 4 over 1, or 4 amps. Here it's going to be 8 over 3, or 8/3 amps. And here it'll be 8 over 6, or 4/3 amps. And notice, my goodness, notice that 8/3 and 4/3, what does that add up to? It adds up equal to 4, right? Because this 4 amps splits up into 8/3 and 4/3 amps. It has to, the junction rule. Okay? This is a little more complicated, but not that much more. Why don't y'all take just a minute? I want you to find the equivalent, and then the, let me think here. Let's make this 10 volts. All right? We'll make that 10 volts. I think that'll work out right. And the answer. Find the equivalent first. The equivalent, and then also what's the current and voltage for each resistor. This is an example of a test question. In a couple minutes I'll jump in and do it on your own. Alright, I'm going to step in a little bit. I'll find the equivalent of this first. 1 plus 2 is 3. And then I find the equivalent of this. We haven't seen this combination, but it works out evenly. 1 over 1 over 6 plus 1 over 3 plus 1 over 2. I know what that is. It's equal to 1, right? So it's 1/6 plus 2/6 plus 3/6. You see, that's 6/6. So 1 over 1 is 1. All right, and then I'm left with a circuit that has 2 resistors. That is 4 ohms and 1 ohm. This is 10 volts down here. And of course, the equivalent of that is 4 plus 1, or 5 ohms. 10 volts. Now I can find the current. So now I start working backwards. I say this current, well, that's 10 over 5. V over R is 2 amps. So I got 2 amps going here through this circuit. V equals IR. So now I want to know the voltage across each resistor. I'll have 8 volts and 2 volts. That's 4 times 2, 4 ohms times 2 amps, 1 ohm times 2 amps. Gives me 8 and 2 volts. And notice they add up equal to 10, which is a good thing. So I can come over here. I have 8 volts here. I have 2 volts here. I have 2 volts here. Now I need to deal with this thing right here, because I know that between these two I have 2 volts. But they split it up, and it's not a nice even split. Like if it was 3 volts, then I could just say 1 volt and 2 volts, but it's not that simple. I mean, there's a fraction involved. So what I want to do is say, I got 2 volts across these 2 resistors. Now, if I have 2 volts across a 3 ohm resistor, that's the equivalent of those two, I would have a current equal to V over R, which is 2/3 amps. So I have a current of 2/3 of an amp going through here, through both of those. That means that I have 2/3 volts, V equals IR, and for this other one I have 4/3 volts. And notice those add up to equal to 2. 2/3 plus 4/3 is 6/3, which is equal to 2. Often on your tests, you'll have nice even numbers and you don't have to deal with fractions, but not always. Sometimes you have to deal with fractions, or use your calculator and do it in decimal form. But you'll see certainly circuits sort of this level of difficulty, maybe even one more resistor thrown in. But I'll try to make the numbers easy as possible. I don't want the math to be difficult. I just want to know that you can take these circuits and tell me what is the current and the voltage in every portion of the circuit. All right. Let's see, I think I have some more practice. Okay, yeah, so let's try this one. And in fact, we'll use this circuit for 4 questions. So first, just find the equivalent resistance of this circuit. Start with the smallest series or parallel, and then move out from there. All right, let's do about 15 more seconds. Stop at 140 or 145, do 145. Go ahead and stop it. Hey, look at that. Y'all are awesome. Right, A is right. You want to take this equivalent, or you can do this one. Either one's fine. This one is 2 ohms. This one is 1 ohm. 1 over a half plus a half is 1. And then I got 2 ohms right here. So in the end, I've got 2 2-ohm resistors in parallel. 1 over a half plus a half is 1. All right? Why did they tell the pig to leave the party? Because his friends thought he was a bore. I think that's funny. That's pretty good. Thank you. All right. So Let's look at the next part of this, and very likely you'll have a series of problems like this. What is the potential across R3? What is the potential across R3? Think about how your voltages are distributed across these resistors. Y'all doing pretty well. A handful of you still don't have the right answer, but feel free to ask your neighbor what they think. All right, let's stop at 115. 115. Just a few more seconds. Just guess if you don't know. Okay, so let's see. Here's B. What was D? 3. Oh, I know why you put D. Yeah, let me show you. So I want to know across R3. So let's not try to write down anything. Let's just try to look at this and sort of reason it out. I know that I got 12 volts across this guy, because this branch and this branch are in parallel with this battery. So between these 2 points, I got 12 volts. I also know that these two have an equivalent that's equal to 1. So these 2 resistors are identical to this resistor. I want to have 2 identical resistors. They split the voltage in 2. Alright, so that means I have 12 volts. That means I have 6 volts. And I got 6 volts across this whole thing. Now some of you put 3, right? Because you thought, oh, I got 6 volts here, so it must split it 3 and 3. But it doesn't. In parallel, so I got 6 volts across this whole thing. I got 6 volts here and 6 volts here. Knowing those rules will help. I mean, just knowing the words of the rules doesn't help, but being able to apply those rules to these circuits. Let me step back through that just one more time before we move on, because it's kind of important. Now, 12 volts between here and here. This has an equivalent to 1, which is identical to this. So I have 2 identical resistors, a 1 and a 1 ohm. Over 12 volts. So that means I have 6 volts and 6 volts. But this one is here, so I have 6 volts between here and here, which means I have 6 volts there and there. So most of the tests, you don't even have to do any calculation. You can be able to look at the circuits and determine the answer. Let's look at, if you removed R3, what happens to the current through R1? If I remove R3, what happens to the current through R1? Does it decrease, increase, or remain the same? All right, let's stop at 40 seconds. 40. It's 5 more seconds. We have a lot of clicker questions today, don't we? All right. All right, good. C is right. C is right. Because when we're looking at R3 and R1, this whole branch of the circuit right here acts independently of this branch. I can get rid of this thing altogether. It's not going to affect this at all, because these are 2 parallel branches. One does not affect the other one. Now the next question has to do with current. We had a similar question in the concept test. Which resistor has the least current traveling through it, at least of R1, R3, or R5? Or do they all have the same current? All right, let's stop at, let's stop 45, 45. I'll go to 50, 50. All right, good. B, I think, is right. Let's go double check that. So going back to that circuit. What was B? Was it R3? Yeah, so I have my current. I have whatever my current is here. We had 2 ohms, so we got 6 amps coming through here. That means I'm going to get 3 amps going through here and 3 amps going through here. And then down here, that 3 amps is going to split into 1.5 and 1.5. Come back together and come back to 3 amps. So R3 does have the smallest current, because we can tell what all the currents are then. We got 3 amps, 3 amps, 1.5 amps, 1.5 amps, and is this the equivalent? Oh no, I'm sorry, 6 amps. 6 amps, I'm sorry. So that's 12 volts. So I have 6 amps here. I get 3 amps up here. What? 6 amps up here. And I got 3 amps here and here. And 6 amps here. I'm sorry. Y'all clear with me? Let me just step back. So my equivalent resistance is 2 ohms. 2 ohms at 12 volts is 6 amps. I is V over R, 12 over 2 is 6 amps. So I got a 6 amps coming up here. These 2 branches are identical as far as resistance is concerned. This is 2 ohms, this is 2 ohms. So my 6 amps get split into, did I just get that wrong here? Yeah, no. 6 amps here, and 3 amps here, and 3 amps here. But then this further gets split into 1.5 amps and 1.5 amps. Oh shoot. 3 amps and 3 amps. Ah. I'm very confused now. Oh. Look, now I got 3 amps here and 3 amps here. I got 6. No, the equivalent was 1 ohm, wasn't it? That was my mistake, because this isn't. Yeah, so I got 6 amps up here and 6 amps up here. And I got 12 amps right here. Okay? All right. Just sort of rewind about a minute and a half, and just consider that lost time. All right. We're going to skip this Christmas vacation right now. We might come back to it. It really fits more in with our household circuits. So I want to just get that later when we do household circuits. This will be the last little section that will be on your test. We'll wrap this up on Friday. But Kirchhoff's rules, we're going to look at multi-loop circuits. So you'll see 2 types of circuits. You'll sort of see the combination type circuits, series and parallel, and then you'll see some multi-loop circuits. And they're similar. You apply some of the same rules, like you'll apply the junction rule and the loop rule, but they're going to be a little bit different too. So we have 2 rules. We've already seen them, but let me just reiterate. We have the junction rule, the sum of the currents into a junction must equal the sum leaving a junction. That's my abbreviation. I'll write it out here. So for example, this is my current going in, and these are my outgoing currents, I1 and I2. So for example, if IN equals 8 amps and I1 equals 5 amps, then that means that I2 is required to be equal to 3 amps. And if I have 8 amps here, I have 5 amps here, then I must have 3 amps here. If I don't, that means that I'm losing some current along the way somewhere. Right? Now, if I have less than 3 amps here, they have 2 amps. That means that there's an amp of current that's going out into the wide world where it's not supposed to be. The loop rule, we've seen the junction rule. That was like rule number 4 for parallel parallel circuits. The loop rule is also seen. We saw it for series circuits. The loop rule says that the sum, I'm going to write it a little bit differently. The sum of the potential differences, or I should say the sum of the voltages, across all elements around any closed loop. Doesn't even have to be a complete, doesn't even have to be like the entire circuit, but just any loop within the circuit must be equal to 0. So for example, let's say that we have 12 volts here, and let's say we had 8 volts and 4 volts here. Have we seen that? But now we're going to express it a little bit differently. We talked about how these things have different potential differences. Do I need to go back up, y'all? That's a must be 0, must equal 0. So if you want to write this as an equation, you would say the sum of all the voltages equals 0. And this equation, I didn't write it, but that I equals I1 plus I2. Now we've seen this before, right? We've been using this a lot. But we're going to change it just a little bit, and we're going to start giving signs to our voltages. We've already seen the signs, right? We said that this has a positive or a negative change in potential for a battery. Is this where electrons gain energy? That would be positive. Or is it where they lose energy? That would be negative. They gain it, right? So it's positive. So this has a positive voltage. And then these, the electrons, this is like coming down the hill on the roller coaster. This is where they lose energy. And they scream and they hold their hands up and sometimes they lose their lunch too. So what I would say here is that the sum of the voltages equals positive 12 minus 8 minus 4 equals 0. That's saying that an electron, or a proton, comes along here and gains 12 volts per coulomb, 12 joules per coulomb. Here it loses some energy, and then here it loses the rest of that energy until it comes back to the battery. There are a few other little rules. We'll deal with those on Friday. But you will see multi-loop circuits, but not RC circuits and not household circuits on the test coming up soon. I'll tell you more about that on Friday. Y'all have a great day.